classification on Fano manifolds or varieties with the second lecture by Joaquín Moraga. Please, Joaquín.
Thank you for the introduction. So today I will talk about log-terminal singularities, it will be, this talk, this part of the mini course is sort of self-contained. We will use it later, but it doesn't use anything that I said previously, but we will use it heavily on Thursday. So the first definition will be the definition of a log pair. So a, quote, log pair is a couple x comma delta, where x is a normal quasi-projective variety, is a normal quasi-projective variety, and delta is an effective Q divisor, so meaning that the coefficients can be rational, for which the canonical plus delta is Q Cartier, meaning that some multiple of this is integral multiple of this is an actual Cartier divisor. So the first thing that you may wonder is why I'm trying to make your life more complicated. If we are already struggling with algebraic varieties, why do I throw this extra gadget? So the reason is the following. It's actually very useful to keep track of this delta because it sometimes gives you extra information. For instance, if you want to study an elliptic curve, so E elliptic, and let's say that you want to study an elliptic curve with an involution, for instance, multiplying by -1 on the elliptic curve, then, well, you can think about this as the group Z2 acting on your elliptic curve. And if you take the quotient, what happens is that you get P1, so let's call the quotient pi, and this ramifies over 4 points. So studying the elliptic curve with involution is the same as studying the pair. So let me just write that the pullback of Kp1 plus 1/2 the sum of the 4 ramification points is equal to the canonical, is actually linear equivalent to the canonical of the elliptic curve. So sort of studying this pair, P1 plus 1/2 P plus 1/2 Q plus 1/2 R plus 1/2 S is sort of the same as studying the elliptic curve with involution. So, so maybe this is a first source of examples of log pairs is whenever you quotient a variety, let's say a normal projective variety by a finite group, well, the quotient is just a normal projective variety again, but if you endow the quotient with some boundary divisor, studying this quotient with the boundary divisor is the same as studying the G equivariant geometry of the starting object. So another example, for instance, can be the icosahedral group that I will denote by IH. So it's the group of symmetries of the icosahedron acting on P1. And then when you quotient it, so well, in this case, actually, the quotient is just isomorphic to P1. But this has some pair structure. So if you want to recover the canonical divisor of P1 here, so let's say that the quotient is now called phi. So you have this finite morphism phi of order 120, of degree 120, sorry. If you pull back the canonical of P1 plus 2/3 0 plus 3/4 1 plus 4/5 infinity, then you get the canonical of P1. This is linear equivalence. So studying the pair, P1 plus this divisor, let me just call it D to avoid writing it again, is equivalent to studying P1 IH equivariantly. Okay, so this is some very general statement that works for any variety with a finite group action. So another source of examples for log pairs is a junction formula, right? So if, as we mentioned yesterday, if you have, a, let's say, a smooth projective variety embedded as a hypersurface in X, so let's say S, a smooth projective inside X, a smooth projective, you, a divisor, right? Actually, you don't need them to be projective, but you get the formula that Ks plus S restricted to S is linearly equivalent to Ks. So understanding the pluricanonical sections, or understanding the sections of the canonical divisor of S, is analogous to studying the pair X, S. So this is another source of motivation for log pairs. So let's say that understanding the log pair X, S, understanding the log pair X, S is maybe not equivalent, but it's, let's say in this case, useful to understand S itself, right? So yesterday, Daniela was telling us about, trying to lift automorphisms to birational automorphism of the pair. So this is more motivation of why we work with pairs instead of just working with algebraic varieties. So now let's jump to the next topic, which is singularities of pairs. So how, for instance, how we measure the singularities of this gadget X, delta. So before I jump to the next topic, are there any questions or comments? It's the icosahedral group. It's a group of symmetries of the icosahedron. So it's a group of order 120, and I don't remember the. Yeah. I'm not thinking about it inside SL. I'm thinking it in GL. Okay, so the next definition is the definition of log discrepancies. So let's say that you have a projective irrational morphism. So first, let X delta be a pair. Let X delta be a, I'm using the language log pair. And Y to X, so let's say pi from Y to X be a projective irrational morphism from a normal variety. A projective birational morphism from a normal variety, and then you pick a prime divisor on Y, so E inside Y is a prime divisor. So essentially, in other words, what I'm trying to look at is some divisorial valuation over the variety X, but let's phrase it geometrically. So in the definition of log pair, we ask Kx plus delta to be Q Cartier. So that means that I can pull it back. I can write pull back of Kx plus delta because it's a Q Cartier divisor, and I will get Ky plus delta y, where this one does not need to be effective. So may not be effective. Not be effective. So now I will define the log discrepancy. The quotes log discrepancy of X delta at E is defined to be the following number. So I will denote AE X delta is just, by definition, 1 minus the coefficient at E of this divisor delta Y. So, okay, so the first time that you see this definition, it should make absolutely no sense. Okay, you pull back something, you look at some coefficient, you write negative the coefficient, and that's it. Okay, but let me try to explain in plain words what this invariant is measuring. So first, this invariant depends on the divisor that you choose over your variety, right? So you can choose different blowups, pick different divisors on the model Y, and this will give you different rational numbers, right? By definition, this is a Q-Cartier divisor, so this is a Q divisor, so this has rational coefficients, so this will give you a bunch of rational numbers. Actually, you can produce infinitely many rational numbers for a fixed given pair X delta. If you keep blowing up forever, you will produce more and more rational numbers. Okay, so what is this measuring? So let me try to explain this in words. So this number gets more negative. So let me write this as a remark, which is not it's not very precise, but okay, if I could try to make it more precise, but let's not get in this direction. But essentially, the number A E x delta gets more negative, quotes, more negative as the multiplicity of x delta along the tangent directions corresponding to E gets higher. Get higher. And of course, here in this phrasing, I'm sort of thinking about picking different E's, right? So the more negative this number is, or the closer to negative infinity, it means that the pair x delta has more multiplicity along the tangent directions corresponding to E. So what do I mean? If you can think about an exceptional divisor, so you can think about a general point in the exceptional divisor as being some tangent direction through your singularity. So here you have x, here you have the, let's say, the divisor E, and here you have y, and the general point of E corresponds to a suitable tangent direction. And what do I mean that the multiplicity is high along this tangent direction? It either means that the multiplicity of x along this tangent direction, or maybe of delta along this tangent direction, is rather high. Okay, so if this remark didn't make sense, that's fine. Just take the definition as it is, but this is at least what we're trying to measure with this definition. So let's see some examples in case this remark looks a bit shady, because I'm not being very precise. And I hope that with the examples, things will be more clear. So naively, the expectation is that the more negative these numbers get, the worse the singularities are. And the more positive they get, or positive and larger, the nicer the singularities are. Let's see some examples about this. So if you just take examples, so if you just take the x to be equal to an, and let's, for the time being, let's just set delta to be 0. So let's just take the finite space. And then what we will do is we will blow up the maximal ideal corresponding to the origin. So we just blow up the point 0, 0, 0, 0, 0, n times. So this is the blow up at the origin. And here we have a unique exceptional divisor, right? So which is isomorphic to Pn minus 1. So let's call that divisor E, the exceptional divisor, isomorphic to Pn minus 1. And you know that if you pull back the canonical of An, what you get is the canonical of Pn plus 1 minus n E, right? So this means that the log discrepancy along this divisor E of An, here I should write An comma 0, but let's just keep An. It's equal to n. So, but this is not the only log discrepancy that there is, right? You can keep blowing up points in the exceptional divisor forever, and something that you can observe is that you will produce more and more divisors with larger and larger log discrepancy. So people in birational geometry tends to say that the log discrepancy quotes measure the height of the blow up. In some sense, we expect that it should somehow measure the degree of the equations defining the ideal that you're blowing up. But I think that there are not so many results in that direction. So what happens if we add some lines, right? So let's look at a slightly different picture. Let's take same germ, the smooth point, but now let's add some hyperplanes through it. So let's say that we take now we consider the pair x equal an, and delta will be, let's say, the sum of the coordinate hyperplanes with some coefficients lambda 1 through lambda n. Okay, so what happens when I pull back now? So let's consider the same blow up. Okay, so I'm not changing the notation from the left side of the board. So now if I pull back the pair, the canonical of An plus delta, well, first I can just pull back the canonical. right? So I get the canonical of, why did I write Pn here? Yeah, someone should interrupt me when I do these silly things. Yeah. So canonical of y plus 1 minus ne, but then I have to pull back delta, right? So when I pull back delta, I will get the sum of the lambda i's e, where I goes from 1 to n, plus the strict transform, the sum of the, I will just denote it by hi tilde, so these are the strict transform of the planes on the blow up, right? So you see that the log discrepancy starts decreasing, right? Because now you have to add this number here, so the number gets larger, so the log discrepancy starts getting more negative. So, sorry? Lambda I, h, oh, thank you. Good. So for the students, this was missing. Okay, so in this case, the log discrepancy of this pair, AE of AN plus delta, it's equal to n minus the sum of the lambda i's. Okay, so it will get negative when the sum of the lambda i's is larger than n. So let's do, okay, I start at 35, right? Is that correct? Or? Okay, so, okay, I think these are enough examples, so now let's go with the definition. Okay, so, okay, let's go with the definition of log terminal singularity. So we say that a pair has log terminal singularities if all its log discrepancies are positive. Definition. A log pair x delta has quotes log terminal singularities if all its log discrepancies are larger than 0. Okay, so this means that I have to look at all possible prime divisors on all the possible, let's say, projective irrational morphisms of x, to x. Right, so this seems very complicated, and a priori it does not look like a finite type process. However, it is known that it suffices to check the condition on a log resolution of the pair. So you take a log resolution of the pair, and you just look at the divisors in the log resolution, specifically the strict transform of delta and the exceptional divisors on the log resolution, and this finally many divisors suffices to check this condition. So analogously, we will say that a pair is log canonical. A log pair x delta is log canonical if all its log discrepancies are larger or equal than 0. So as an exercise, larger or equal than 0, as an exercise you can check that this pair x delta, so exercise, x delta is log terminal if and only if lambda I is less than 1 for all I, and is log canonical if and only if the lambda i's are at most 1. Okay, so you can check this condition, and actually to check this condition, probably just doing the first blow-up will suffice, and you will see clearly which divisor you have to pick. So there are other notions. Actually, this notion of log terminals and log canonical singularities are rather newer than their siblings. So we say that a log pair is terminal. A log pair x delta is terminal without the log if all its log discrepancies are from exceptional divisors, so meaning that divisors that do not live on X itself, so divisors that are in the exceptional loci of this projective irrational morphism Y2X, exceptional divisors are larger than 0, and we say that a log pair, I'm writing too many times the same things, but sorry, I'm almost done. A log pair X delta is canonical if all its log discrepancies are larger or equal than 0. Oh, wait, sorry, this is 1 and larger or equal than 1. If all its log discrepancies are larger or equal than 1. So let me explain where this word comes from. So we have defined these 4 terms: terminal, canonical, log canonical, and log terminal. So actually, these words come from the minimal model program. So let me not get into the details, but let me tell you how these names were born. So essentially, if you have a smooth projective variety, and let's say that the canonical divisor has some sections, so X, a smooth projective variety. So this is just a historical note, okay? It's not X smooth projective. And let's say that Kx is big. I don't know. I don't need this too. I really don't need this. But then there is this expectation that you can perform a variational modification called minimal model program to a new variety that may not be smooth, but Kx prime should be big and nef. Okay, and this variety here may be singular. Okay, so there are examples in which this variety X prime, in which the canonical divisor becomes big and nef, is singular. Okay, so essentially, this is what we call the minimal model program, and the idea is that you pay some price. The price is introducing singularities, but what you get in reward is that you improve the positivity of the canonical divisor. And this variety is the last step of this program, so it will be called the terminal model or the minimal model. So terminal singularities are the singularities appearing in the terminal model. So that's where the name comes from. So terminal singularities are the singularities appearing in the terminal or minimal. Nowadays, I think people mostly call it minimal model. But I think when it was started, people would call it the terminal model. Okay? And then you can take the ample model of X prime. So you take the same X, and then you take X prime, and then you can take the ample model, because if the canonical divisor of a mildly singular variety is big and F, there is a theorem due to Kohler that tells you that it's semi-ample. So it defines a birational, projective birational map to a new variety X prime prime, which is called the canonical model. It's called the canonical model because this variety is also the proj of the sum m larger or equal than 0 of h naught x. This X prime prime is isomorphic to the proj of all the pluricanonical sections of X. So that's good. And this is what we call the canonical model of the variety X. And then the canonical singularities are the singularities appearing on this X prime prime, the canonical model. So canonical singularities. So this is canonical singularities are the singularities appearing in the canonical model. Can you repeat that? So I will get there in a second. Yeah. So in dimension 2 there are no terminal is the same as smooth. Yeah. But that's terminal, not canonical. Yeah. That's correct. So, and then what is log terminal, log canonical? Well, this word just starts for logarithmic. So it's like the logarithmic version of the other two terms because you are allowing certain poles of differential functions to have at most simple poles, okay? So that's more or less the, yeah, so those are the definitions. And now let me tell you a little bit about, well, let's see some examples. So the classic example is the following. So if you take a smooth point and you take a finite group acting on it, then you can consider the quotient, right? So when I say that a group is acting on a point, I mean that it's fixing the point. And you can take the quotient, and this is likely, it will likely produce a singularity, right? Because, for instance, it will change the multiplicity of the germ and, well, many other invariants. So it's most likely than not that it will be singular. So there are some theorems that tell you when it will be smooth, but let's, well, I can mention that later. So example, so you take G acting on a smooth germ, let's say AN 0, and then you take X to be the quotient, AN quotient by G. So my claim is that X has log terminal singularities. So X has log terminal singularity. So let me tell you how you prove this. So the idea is that you take any projective irrational morphism, extracting some prime divisor E from Y to X, and then you can G equivalently compactify this picture. This is the quotient by G. I mean, you can take pullback of the diagram and look at normalize or something, and then you will get a birational map to AN, and here a quotient by G. And we know that AN is log terminal. So all the log discrepancies of AN are larger than 0. So in particular, if you look at any preimage of E here, let's call it E tilde, I mean, there could be more than one preimage, right, because it's a finite map. But if I look at the discrepancy along E tilde, then this number must be larger than 0. And what you can compute is that the log discrepancy of X at E, it's equal to the log discrepancy of AN at E tilde divided by R, where this is the ramification index of the map from Y tilde to Y at the generic point of E. So this is some ramification index. And how do you prove this formula? This is just Riemann-Hurwitz. You just write Riemann-Hurwitz, divide and factorize, and ramification index. And you get this formula. Well, but this is a, oh wait, I swapped the, oh no, that's fine. So this is a positive number divided by a positive integer, it remains positive. So we prove that all the log discrepancies of the quotient are positive, hence every finite quotient singularity is log terminal. Are there any questions before I move on? So this gives a lot of singularities of log terminal. Sorry, this gives a lot of examples of log terminal singularities. And then you may wonder if I can give you an example of something that is log canonical but is not log terminal. So there is a classic example, which is cones. So, oh, it's any projective morphism to X, right? So we're trying to measure this invariant called log discrepancy, so I just fix any projective morphism down to X. I complete it equivariantly, right, by taking the fiber product and normalizing, if necessary. And then I have G acting here. So Y is indeed the quotient of some projective, equivariant projective irrational morphism to AN. So that's the idea. So another source of examples are cone singularities. So if you have a projective variety with an ample divisor, you can take the cone over it, so essentially pretty similar to this construction, but without the proj. And this will give you, well, most likely than not, it will give you a singular point. It can give you a smooth point too, but if it gives you a smooth point, it's essentially you're taking the projective space and the class of a hyperplane. So let me write this new example. Let me actually write it as a proposition. The proof is actually very similar to this picture using a junction. So let me write the following proposition. So let X be a smooth projective variety of Picard rank 1 with rho of X equals 1. So you can write a more general statement, but let me just pick the Picard rank 1 case, and H be an ample divisor, H an ample divisor on X, and then we will take Cx to be the cone with respect to that polarization. So I will take X to be the spec of the sum m larger or equal than 0, H naught X OX MH. And this will give you a singularity with a vertex, right? There is the maximal ideal corresponding to all the positive summands here. So I will just call this 0, or let's call it B of vertex, right? So the singularity Cx comma B, or Cx, well, let me write the statement like this. Cx is log terminal if and only if X is Fano. Cx is strictly log canonical. I will explain this in a second. If and only if X is Calabi-Yau. So what strictly log canonical means, I think I had to mention this before, but I forgot. So this is, well, by definition, let's write def, LC, not LT. So log canonical, but not log terminal. Okay? This is what we call strictly log canonical. And Cx is not log canonical if and only if X is canonically polarized. So essentially the trichotomy, canonically polarized. So essentially the trichotomy that I explained yesterday of smooth projective varieties, that they can be classified, or well, not classified all of them, but they come from these three pure classes, right? Fano, Calabi-Yau, and canonically polarized. Essentially these statements that I wrote here, log terminal, strictly Calabi-Yau, and not log canonical, log terminal, strictly log canonical, and not log canonical, are like the local analogs of Fano, Calabi-Yaus, and canonically polarized varieties. So let me say that whenever we prove something in one of these classes, there should be a corresponding local statement of the theorem that you're proving. Okay? I don't know what is the local statement. It depends on the theorem. And sometimes you have to tweak it a little bit. Okay? But, and we will see examples of that soon. But there is a lot of, let's say, local and global principles between these projective varieties and these classes of singularities. So are there any questions before I move to the next topic? Yeah. So, okay, so let me tell you what we know about these singularities. So let's talk about classification of log canonical singularities, or worse than log canonical singularities. Yeah, before I jump to the classification of, or what we can say about the classification, let me just give you a second exercise. So for the students' exercise, so you take a hyper surface singularity in AN. If the multiplicity at the origin of H is larger than n plus 1, then H, 0, so the hypersurface singularity at the origin, is not LC. So you remember that there was this idea in hypersurface, projective hypersurfaces, that large degree are canonically polarized, degree n plus 1 are Calabi-Yau, and low degree, less than n plus 1, are Fano. So there is something similar on this side. So essentially, if you look at hypersurface singularity, you have the expectation that high multiplicity is not log canonical, some multiplicity close to n plus 1, whereas n is the dimension, should be log canonical, strictly log canonical, and less than that will be log terminal. But let me say that the picture is much more complicated. It's not an if and only if. There is a lot of constraints to really make this statement precise. Okay? So So now let me tell you what we know about this singularity. So the first person that, well, not the first, but one of the persons that studied canonical singularities for surfaces was Artin in a paper about obstructions for adjunction. So dimension 2. So let's start with this. So let me just mention that there is nothing interesting in dimension 1, right? Because I'm assuming that my underlying variety is normal. So in dimension 1, you just get smooth. Well, we can write here dimension 1 first. It's not very interesting. But in dimension 1, essentially what we are looking is just A1 with lambda 0, right? Because we're looking at normal curves, so they're all smooth. So essentially, this is locally, like analytically, locally, this is the only example of a log pair singularity for dimension 1. And this is log terminal if and only if lambda is less than 1, and this is log canonical. Well, I actually explained this example already, right? I did it more general. It's log canonical if and only if lambda is less than equal to 1. So now let me tell you what we know in dimension 2. And in dimension 2, I will drop the pair because it gets much more complicated. So I will just work with a Q-Gorenstein singularity X. So in dimension 2, we can say that X at the point X is terminal if and only if it is smooth, is canonical, if and only if it has ADE singularities, and is log terminal if and only if it has a quotient singularity, so orbifold point if you want, quotient singularity, and is log canonical or strictly log canonical. Let me write this case, strictly log canonical, that as you notice I'm abbreviating as LC, if and only if it is an elliptic singularity. Okay, so essentially it pretty much looks like the cone over an elliptic curve or the cone over a chain of rational curves. So what I want to say with this is that we can, and I mean this is very classical work. I don't know if I should attribute it to anyone, but all these notions are, let's say, very well understood in dimension 2. Okay? So then we have the following, I mean, I can tell you what happens in dimension 3. So in dimension 3, there is a big result by Miles-Reed that classifies terminal threefold singularities. Let me not write the whole table because it will be a little bit long, but essentially what the theorem tells you is the following. So theorem by Miles-Reed, I think this is early in the 80s. So Miles tells you that a terminal threefold singularity XX is a hyperquotient singularity. So what is a hyperquotient singularity? It's the quotient of a hypersurface singularity. So you take a hypersurface singularity with a finite group action and you quotient by it. That's what we call a hyperquotient singularity. And Miles not only tells you that terminal threefold singularities are hyperquotient singularities, but he tells you all the hypersurfaces that may appear, and there is a finite list up to analytic change of variables. So essentially, what this theorem says, it says that we can classify all terminal threefold singularities up to taking some suitable cover, right? And then if you look at this table, something very similar happens here, right? I mean, all log terminal singularities are quotients, are finite quotients. So they are quotients of a smooth point. So up to covers, they're just smooth, right? So then you may wonder, is this true that we can classify log terminal singularities in every dimension up to finite covers? And the answer is sadly no. But before I get to the theorem, let me define one more thing. So I've been using the word quotient a lot, so let me define the following object. So let x be the germ of a normal singularity of a normal singularity over the complex number. And then you will take a very small epsilon, so epsilon larger than 0, small, and consider the link of the singularity, which is defined to be the intersect. Oh, sorry. Yeah, epsilon is small. No, I'm not sorry. I didn't say anything wrong. So you take S epsilon intersected with X, where S epsilon of X is a sphere of radius epsilon around X in some ambient space AN. So you embed your singularity in some affine space. Well, it could be just like a neighborhood, analytic neighborhood of the origin. You don't need the whole affine space. But you embed your singularity, you look at the point that you're studying, and then you look at a very small sphere around the point, and you define the link to be this object. So here, what is the natural complaint? There is no epsilon on the left, right? So the point is that this object is independent of epsilon up to homotopy. If you pick epsilon sufficiently small, this was proved by Milnor in his paper about Milnor fibers for isolated singularities, and later generalized by Durfee in the case of non-isolated singularities. So we have some topological object, right? It's not necessarily a smooth manifold because I'm not saying that the singularity is isolated, but we have some topological object that captures the singularity, or yeah, that captures the topology around the singularity. So the local fundamental group of X, the quotes, local fundamental group of X at X is just the fundamental group of the link. And all these things are path connected, so let me not fix a point. It will just make things messy. Okay, so this is what we call the local fundamental group of the singularity. So we can rephrase this statement as saying that the terminal threefold singularities with trivial fundamental group, with trivial local fundamental group, are hypersurface, right? So if you want to study singularities up to finite covers, essentially what you need to do is just look at the ones that have trivial fundamental group. Or if you want to be, okay, if you want to be a bit more precise, the ones that have trivial profinite completion of the fundamental group. But okay, let's not get into so many details. Let's just say that now we want to, so a natural aim will be to classify log terminal singularities with trivial local fundamental group, right? That will be a natural aim. Because in dimension 2, there is only the smooth point. These two have non-trivial local fundamental group because they are quotients. And here, there are only hypersurface singularities because, well, the others are quotients of hypersurface, right? So this is a very natural goal. And I think that around the 90s, there was some group of people trying to prove some statements in this direction. And then Kohler proved the following theorem. Sorry, which one?
The last one. Because I think there are strictly local manifolds which are not elliptic and varieties which are not strictly.
It depends on your definition of elliptic singularities. For me, no, but I'm thinking that the exceptional could have genus 1 but have many irreducible components. So.
No, but you have a rational you have like 4 or 3 things and like so.
Yeah, sorry. Let's say elliptics plus some other finite cases. Yeah. Here there is some extra things. You're totally right. I was thinking about the non-rational ones, but there's some finite case, finite many families. Finally, many families. Okay, let me not get into this detail. So what was the expectation? The expectation was that we maybe could classify all log terminal singularities up to finite covers. So in other words, classify log terminal singularities with trivial local fundamental group. And in this direction, Kohler proved the following theorem in 2010. So there is a sequence. There is a sequence. Let's call them XR at 0 of terminal fourfold singularities. So terminal, right, is the mildest case, fourfold singularities with embedding dimension going to infinite. So in the sequence, right? The fundamental group being trivial and the class group being at the class group of the localization at the point being trivial. So I will explain why this condition is important in a few minutes. But essentially what Kohler is saying with this example is that there is no hope to classify terminal fourfold singularities, because there is a sequence of terminal fourfold singularities whose embedding dimension is getting arbitrarily large, so it's impossible to write a finite list, but you cannot improve them with finite covers. And then I will explain why this condition plays an important role, but I will explain that in a second. Okay, so let's see. So let's draw a table with, okay, let me just redo this.
What's the embedded definition of the hyperquotient singularities of the previous current?
The embedding dimension of this one can get arbitrarily large, right? But the point is that they are hyperquotients, so they have a cover that has embedding dimension 4, right? Because the hypersurface one has embedding dimension 4. So the hope for a few years, the hope is that we could classify terminal singularities with trivial fundamental group, but Janos say no, it's impossible. So let's draw a little table. So in dimension, terminal, canonical, log terminal, and log canonical. So I will use some abbreviations. So in dimension 2, 3, and 4, so here you have only smooth points. Here you have the ADE singularities. Here you have quotient singularities. And here we say that we have elliptic singularities and other finally many families. Singularities plus finally many families. In dimension 3 here we have hyperquotient. And I have to say that up to now we have no clue what is here. We have no clue what we should write here, and even less clue of what we should have here. And here it is simply impossible to classify. There is no way that we can write something reasonable in the fourth line, because already in the smallest class you have singularities of arbitrarily large embedding dimension, right?
One small question. You are making a relation between quotient singularities and pi 1. So for you, quotient is what? The points with non-trivial isotropy are isolated, or?
No, just quotient. I mean, wait, I think I said it, but I mean, assuming that G fixes the point, and then you just quotient it. But I'm not asking about isotropy in nearby points, so it could be non-isolated, and could be, yeah. So
It's clear that then the fundamental group is non-trivial?
the fundamental group will be a homomorphic image of G, and then you just have to quotient by the normal subgroups generated by the isotropic groups in the codimension not maximal, right? So yeah. Are there more questions? How you find them? Oh, this is the local class. Is the class group of the localization at the point. Yeah. So yeah. So let me keep going. So let me mention one more definition, and then I will do some connections with what I was mentioning yesterday. So essentially, okay, so far everything I have said is the following. So there is these singularities that we care about in algebraic geometry that we call terminal, canonical, log terminal, and log canonical. So these are some singularities that appear naturally in birational geometry. And so that's the first thing that you have to remember. And the second thing is that in low dimensions we have some classifications, but in dimension at least 4 is impossible. Okay, so what we do instead, we try to do some qualitative study of these singularities, right? I mean, if you cannot find the equations explicitly one by one, at least maybe you can tell me how they look, how they behave, right? Something more qualitative without getting to the actual equations. So that's what we will get into now. So more qualitative descriptions of log-terminal singularities. But let me just mention one more thing before we get to these qualitative descriptions is some further definition. So, and this is a word that I will be using quite a lot. So definition, a singularity XX is quotes, is of quotes log terminal type. Okay, so this sounds a bit long, but that's the notation that we use. Terminal type. If there exists delta effective such that x delta x is log terminal. Okay, so let me just make a remark about this, is that the boundary divisor is something that we use a lot in algebraic geometry, and some possible use of this boundary divisor is like you can think about it as a correction term sometimes. So maybe your singularity is not Q-Gorenstein, but you can add a little bit of some boundary through the singularity to make it Q-Gorenstein. Okay, so let me write this as a remark that the boundary divisor could be used as a correction term for the lack of Q-Gorensteinness. The delta can be used as a correction term for the lack of Q-Gorensteinness, which is a word that I don't know if it exists, but okay, makes sense. So example. So I'm not going to get into the questions of this example because it has too many equations. It's not a complete intersection. But if you look at the cone, so I will use notation from toric geometry. So if you don't know toric geometry, I'm sorry. You can ask Fernando Figueroa to explain you all the details afterwards. So if you look at this, cone, these cones correspond to something that we call a toric singularity. And a toric singularity is Q-Gorenstein if and only if there is a hyperplane containing these three elements on the space, right? And it's clear that no hyperplane contains the three of them, because if a linear function has value 1 in these three, then the value at this one will be 3. So there is no plane containing them. Okay, so the corresponding singularity x sigma is not Q-Gorenstein. It's not Q-Gorenstein. But then if you take the pair x sigma and then you add something like 2/3 d4, where this is the divisor corresponding to the last ray, then this singularity is log terminal. So this is a theorem in singularity theory that tells you that actually all toric singularities are log terminal type. They are not log terminal because they may not be Q-Gorenstein, but they are log terminal up to adding some part of the toric boundary with some suitable coefficients. Okay, so let me write this theorem. So what are toric singularities? Well, toric singularities are simply quotients of a smooth point by a torus, an algebraic torus acting linearly on the smooth point, right? That's one possible definition of toric singularity. So let me first write the theorem that I just mentioned. So the theorem, and you can look at the book. I think this should be contained in Cox-Little-Shank toric varieties. I will be too surprised if it is not contained. So a toric singularity is log terminal type. And as I said before, let me write this as a theorem because it's not entirely trivial from the definition, but actually you can prove it using the things about Cox rings that Michela was mentioning yesterday. So a singularity. Questions? a singularity XX historic if and only if it is a torus quotient singularities. So meaning the quotient of an algebraic torus acting linearly on a smooth point. Torus quotient singularity. Maybe I don't even need to assume the linearity of the action using Lunetal slides, but okay, let me just write this. So, and let me write one more theorem, and this should be attributed to Álvaro Liendo and Hendrik Suess. So what we know from these two theorems, so first let me make a remark. So let me make a remark, and then I will get to the Liendo-Suess theorem. So the remark is that finite quotient singularities are log terminal, right? So this is something that we sort of proved today. And then from these two statements, you get that torus quotient singularities are log terminal type. May not be log terminal, but they're log terminal type. So torus quotient singularities are log terminal type. Okay, so then the question is, well, can we push this a bit further? For instance, if I have a torus acting on a log terminal type singularity, is the quotient log terminal type? And this is a theorem due to Liendo and Suess in around 2005. That if an algebraic, so let T be an algebraic torus, acting on a log terminal type singularity XX, log terminal type singularity XX, then the quotient, X quotient by the torus, and the image of the point that I will just denote by X bar is log terminal type. Okay? So essentially, you can say something much more general than the second statement, right? The second statement tells you that if you have a torus acting on a smooth point, then the quotient is log terminal type. But you can start with any log terminal type singularity. And in 2022, with three co-authors, with Daniel Greff, Lucas Brown, and Kevin Langlois, we proved the most general possible statement that log terminal singularities are preserved under quotients by reductive groups. And I think this is the best that one can prove in that direction, because if you quotient by a non-reductive group, then the quotient may not be even be Noetherian. So it's not a normal projective variety. So this is a theorem that we proved in 2022. So that Lucas Brown, Daniel Greff, myself, and Kevin Langlois. No, Kevin goes first, right? And I go at the end. That kill log terminal type singularities are preserved by reductive quotients. Okay, so if you know Boutot results in 1970 that says that rational singularities are preserved under reductive quotients, this is sort of the MMP version of that statement, that rational singularities are preserved under reductive quotients. Okay, so this is, for instance, one. So I mean, what is nice about these results is that it gives you a huge source of log terminal singularities, right? With very, let's say, interesting equations, right? I mean, if you are into representation theory, there is like a complete classifications of representations of SLN with the condition that the ring of invariance is a complete intersection, right? There is a classification for every n. There is finally many equations, and you know, just using that for each n, you get a plethora of different log terminal type singularities by applying the previous theorem. Okay, so And then if you look at, I mean, that's only if you look at a complete intersection representation, meaning that the ring of invariants is a complete intersection. But if you look at crazy representations, you get more interesting things. Even with SLN, you can produce. Now, using this term, with SLN, you can produce infinitely many log terminal singularities. OK, so are there any questions before I jump to the next topic?
So, is the action that you're using linear, right?
I think we don't need to assume. I mean, since we're working on a germ, we can use Lunetal slice to assume that, to say that it's sort of the quotient will be isomorphic to a linear action of G. So we don't need to a priori assume any linearity. So it could be acting highly nonlinear on a projective variety and fixing a point, but then you apply Lunetal slice and then you assume that at the point it's acting linearly. So that's step one of the proof. So you got you got in the right direction. So let me just make a remark here, right? Because we have discussed reductive groups, algebraic tori, and finite groups throughout this talk, right? So let me make a remark about torsors over singularities. So the reason why I wrote SLN here is because, right, I mean, we have mentioned finite groups, we have mentioned algebraic tori, and SLN is sort of the simplest semi-simple group. And you know, these three groups build all reductive groups by, you know, products, extensions, covers, and so on. So let me write a remark here, is that if you have a singularity and then you want to understand finite quasi-torsors over the singularity, finite quasi-torsors over XX, what you need to do is to look at the finite completion of the fundamental group of the singularity. Okay, so this finite quasi-torsor over XX is a very fancy way to see that you are thinking about like a G bundle where G is finite, but it may degenerate at some special points, right? So some fibers may be quotients of G instead of the whole G. Right? So if you delete the word quasi, then it's just a G bundle. If you add the word quasi, it means that it's a G bundle on codimension 1, and then in higher, well, codimension 0 as well, and then in higher codimension it may get some nasty fibers, but still somewhat related to the finite group. So torus quasi-torsors over the singularity. Well, if you want to understand torus quasi-torsors over the singularity, the same picture, the general fiber is an algebraic torus, and some special fibers may be quotients of this algebraic torus, then you have to look at the local class group. So what do I mean with this? If this object is trivial, then there is no finite quasi-torsor which is not a torsor. If this object is trivial, then there is no torus quasi-torsor that is not a torsor. And then if you want to understand semi-simple quasi-torsors over an algebraic singularity, you have to look at, I don't know what, I mean, this is something that, I mean, even if you look at semi-simple torsors over curves, it gets much more complicated than the finite. I mean, finite torsors over curves are finite covers. Torus quasi-torsors over the curves are like GM bundles, right? Those are easy to understand, but for instance, even SLN torsors over curves are complicated. We don't know yet what you have to write on the right side. So going back to the theorem by Kolar, so remember that the theorem by Kolar tells us that this sequence of terminal fourfold singularities that he built have trivial fundamental group and trivial class group. So in other words, what he was trying to say is that those singularities cannot be improved by finite covers and cannot be improved by GM quasi-torsors. So that's essentially what he was trying to express with these two equalities. Okay, so far, let me just summarize what I said. So first, we define these classes of singularities that appear in birational geometry. Then the second thing that we said is that it's impossible to classify them, but we can get a lot of examples. Okay, so this is the summary of everything I have said. So now we will get to the last part of the talk, which is some positive result, right? So far we don't have many positive results about these singularities. And okay, let's get to it. So let me start with this theorem by Camille Jordan in the 1870s, which many of you may know with the name of Jordan-Schurter lemma, or maybe some other name. So theorem, Jordan in 1870s. So it says the following. So there is a constant Cn satisfying the following. Let G be a final group of GLNC, be a final subgroup. Then G admits a normal abelian subgroup of index at most this constant that only depends on the dimension. So how do you, how can you express this theorem? Essentially, it says that finite subgroups of GLN, you fix n, and then you look at finite subgroups of GLN, and they're essentially all, they're almost abelian, right? They may have some non-abelian part, but it's small. It's controlled in terms of the dimension. So there is a theorem by Collins a few years later, in 2010, that says that Cn is equal to n plus 1 factorial, provided that n is larger or equal than 71. So if you are wondering why 71, symmetric groups of order less than 71 are quite pathological from the perspective of representation theory. They have some sort of unexpected representations. And this is the reason why the 71 shows there. And the reason why it took so long from this previous result is because you need to use classification of simple finite groups. So you need to dig deep into some details. Yeah. So this one is optimal. It's the symmetric group acting on, It's the symmetric group acting on a smooth point. So you can rephrase this theorem as follows. Let me just rephrase. And something interesting about this theorem by Camille Jordan is that the proof uses no group theory. Actually, it follows from the existence and uniqueness of a partial differential equation. And it was sure, 50 years after this theorem was proved, it was sure who realized that the uniqueness and existence of these partial differential equations implied these statements about subgroups, finite subgroups of GLN. There is some symmetries inside these differential equations that Camille Jordan was looking at, and that's where the G comes from. But I think this theorem was essentially proved many, many years before people realized that it was proved. You have to take the symmetric group, but not with the standard representation. Essentially, you look at the projective space, and then you look at the symmetric group acting on the hyperplane defined by all the equations adding equal to 0. Okay, so let me just rephrase. Let me write a corollary that was also probably realized much later. So let XX be a n-dimensional quotient singularity. So orbifold point be an n-dimensional quotient singularity. Then the local fundamental group admits a normal abelian group of index at most Cn. And then this Cn is always the same constant. So let me tell you how you prove the corollary from this. And it's not entirely trivial. It's almost trivial. So the proof is the following. Well, you know that X is a quotient singularity, so you have G acting in Cn, and then X is just Cn quotient by G, but this doesn't mean that the fundamental group of X at the point is G, right? But it's a homomorphic image, right? Because this guy minus the origin is simply connected. So we get a surjective homomorphism from G to the local fundamental group of the quotient singularities, and then we're done. Because here we have a large normal abelian subgroup, and then, of course, this statement is preserved under surjective homomorphisms. Okay? So we have this corollary. So something that we prove in 2020 is the following theorem. So this is with Filipazzi. So let me keep this one. So let me erase the proof. So did we all follow the proof? Surjective homomorphism, and then you're done. Inequality. What do you mean that if this
Because you're saying like Cn is bounded, the index is bounded by Cn, but is it interesting to think about this is equal or not?
Okay. So I guess you're wondering if there is any like characterization of the equality case. So yes. So actually, you can say that. Yeah, but that's a. Yeah, so the answer is yes, in the sense that it is interesting, but I don't know what singularities you will get that hit the bound. Yeah, that's a fair question. So let me state the following theorem, which is due to Lucas Brown, Stefano Filipazzi, myself, and Roberto Sbaldi. And this is 2020. So there is a constant. Let's call it Kn now, because it's different from this Cn. Kn, only depending on n and satisfying the following. So let Xx be a log terminal singularity of dimension n. Of dimension n, then the local fundamental group of the singularity admits a normal abelian, a normal finite abelian subgroup of rank at most the dimension, so rank at most n, and index at most Kn. So in particular, the fundamental groups of these singularities are finite groups. And then it satisfies precisely the same property than quotient singularities. However, we do not get the same constant. Like this constant, we need to use boundedness of Fano varieties that I will explain on Thursday. So it uses some black box, right? That just tells that there exists some number. And then essentially the statement is the same. So as a consequence, well, actually this was known before we proved this, but the fundamental groups of log terminal singularities are finite. And then they have the same shape than the fundamental groups of n-dimensional quotient singularities. So some statement that something that I don't know or I do not understand yet is if you give me an n-dimensional quotient singularity and you give me an n-dimensional log terminal singularity, I don't know any topological invariant that can tell them apart. So it could be that topologically they're very similar. And this statement tells you that. I mean, it tells you that at least from the perspective of fundamental group, you get almost the same things. It is true that Kn is slightly larger than Cn, but it's rather negligible. the difference. I mean, both of them grows exponentially, so it's not something. I mean, they don't have different asymptotics. Yeah. So yeah, let me mention a last theorem for today, which actually was proved 1 year after this one. And let me see if I have time to define one more thing. Okay, I'm in the last 10 minutes. So let me think. Yeah, so I will define this because I need to use it tomorrow. No, not tomorrow. Tomorrow I'm not talking, but on Thursday. So any questions about this statement? Oh, the least number of generators. Yeah. And let me mention that here you get that the rank is at most n trivially because it's an abelian group acting on Cn, so it linearizes. Right? But here it was actually very hard to control the rank. So let me just summarize saying that, at least this part, let me just summarize saying that topologically we cannot distinguish log terminal singularities from quotient singularities. I don't know any topological invariants that can tell them apart, like honestly. Maybe I can tell apart 2 examples with some topological invariant, but not. So given a log terminal singularity, I don't know topological invariants that will tell me that this is not quotient. That's the precise term. So now I will throw a few more definitions at you and then a last theorem. Sorry? Is we don't know. Yeah, so so we know that it's larger for some small values of n, but we don't know if asymptotically they differ. Right? So there is all these issues with representations of symmetrics in low dimensions that messes all these pictures. But okay, so let me give a few more definitions and then a last theorem, which is a sort of generalization of this one. So let x delta be a log pair. The regularity, and I will come back to these definitions on Thursday, so don't worry if I go a little bit too fast. So the regularity of x delta is the following invariant. So this is very long and it looks scary, but it is what it is. So it's the maximum k such that there is a log resolution y delta y to x delta. Let me write it diagonal, otherwise it doesn't fit. And k distinct components of delta y equals 1. So all the components of delta y that have coefficient 1, S1, Sk, with non-trivial intersection. Okay, this definition should make very little sense. Okay, so it's something that looks very unnatural. But essentially, let me explain in words what this means. Is how difficult is the resolution of singularities combinatorially speaking? Like the resolution of singularity will correspond to some sort of CW complex, and this is measuring the dimension of that CW complex. And then I subtract 1 because, okay, I want some invariant to move between 0 and n. But okay, let's get into that later. So. Yes, that's what I will mention on Thursday. So this is the regularity of a pair, and now the absolute regularity of a log pair, the absolute regularity of x delta is the following invariant. So I will write reg, but now I will write a hat. So sorry, this is the definition. So I should write these 2 points. So the absolute regularity of a pair is the maximum regularity of x delta plus b such that x delta plus b is log canonical. Okay, so let me just explain in plain words what this absolute regularity is about. It's like, it's in some sense a way to measure how far is the singularity from being toric. It's a very coarse measurement because it doesn't really tell you if you're toric or not, but at least it tells you how many hyperplanes can you pass through the singularity, like hyperplanes with coefficient 1. Right? And in a toric singularity, you have a lot of, quote, hyperplane sections that corresponds to the torus invariant divisors, and you have as many, at least as many as the dimension. Right? And this definition essentially measures something towards this direction, like how many hyperplanes with coefficient 1 can you pass through your given singularity, and the regularity will take, the absolute regularity will take values between -1 and the dimension -1. So now let me finish with the following theorem, which I proved in 2021. So, oh yes. So it's an effect. So this is a log pair. So B must be effective. Oh, but maybe you can subtract. So yeah, I should say that it's effective because. Yeah. Thank you. So let me finish with this theorem that when I proved it back in 2021, I realized that toric geometry controlled log terminal singularities quite a lot. So it's very similar to the one that I'm erasing, and that's actually something that sort of uses the ideas of the proof of this one. But it's slightly different. So the theorem is the following, and this is much more geometric. So theorem M21. So let XX be a n-dimensional log terminal singularity of absolute regularity or of absolute regularity R. So this R is between, we say, -1 and n-1. Okay, so you fix the dimension of your singularity, and then you fix the absolute regularity, which is whatever this invariant here is. Okay. So then there exists an analytic embedding of a puncture disk to the r+1 power inside the smooth loci of the germ, such that the image of the induced homomorphism so you have pi1 of the puncture disk to the r+1 power, which is just set to the r+1, to the local fundamental group, is finite, normal, and of cokernel of order at most this Kn that appeared in the previous term. So essentially what I'm trying to tell you is that, so we have this abelian group, this large abelian group inside the fundamental group of a log terminal singularity. This large abelian group does not come from thin air, right? This doesn't appear magically flying in the proof. It actually comes from the image of an analytic disk near the singularity. So, or not the product of some analytic disks. So essentially what this is saying, or the way that the interpretation that I give of this term is that the fundamental group of a log terminal singularity is sort of controlled by some, maybe not toric geometry, but near toric geometry, right? You have this disk embedding in the smooth variety. The projective picture that you will imagine is an algebraic torus embedding into some projective variety, right? But this is an analytic picture. So the proof of this theorem uses a lot of boundedness of Fano varieties that I'm going to explain on Thursday. And essentially, the main difficulty is constructing this embedding, or this embedding of this analytic tori. But okay, so So let me just summarize. I think I started a few minutes late, so okay, I'm fine. I still have 2 minutes, even if I started at the time. So let me just summarize what we did today, and we will finish with this summary. So, you know, I mean, this is not really toric geometry, right? Because I'm not telling you anything about this embedding. It's just a disk of some dimension embedding near the singularity. There could be zero toric geometry, but this motivates the question is, you know, like, it's very similar to what I was discussing yesterday, that maybe instead of doing toric geometry, we have to do something slightly more general, and then we will see much more, okay? So let me just summarize what we did today. So we define log-terminal singularities and some other classes, but we're not going to talk a lot about them. So summary. 1, definition of log-terminal singularities. Then we say that log-terminal singularities cannot be classified. Log-terminal singularities cannot be classified. So this was the second philosophical statement that was made precise by a theorem due to Collar. Then we mentioned that reductive quotient singularities are log-terminal type. So this means that we can produce a lot of examples in each dimension. And the last thing that I wanted to mention with this theorem is that the fundamental group of log-terminal singularities, the fundamental groups of log-terminal singularities is controlled by toric geometry. Well, it's not toric, let's say near toric or something like that, but it's controlled by toric geometry. And after writing toric geometry, let me write the word near here. Right? It's not precisely toric geometry, it's some sort of analytic toric geometry. But you know, this philosophy of trying to find algebraic tori to explain things inside algebraic varieties is very common, right? This has to do with the SYZ fibration, it has to do with the Gromov-Witten invariance, with mirror symmetry, and many other things. So the perspective that we will start taking from now in this mini course is we successfully use near toric geometry to understand the fundamental group of log-terminal singularities. Can we use it to classify Fano varieties? That's what we will try to do on Friday and Thursday. Okay, I will stop here.